Hello, I'm Graham. I'm with Expero. I do data science of various flavors. The flavor we'll be discussing today includes deep learning, graph, what else? I don't know. We're going to get back into the presentation and see. But I will say that we do, as Matt mentioned, partner a lot with Data Geeks, and we're excited to be here tonight. And I had the pleasure of giving away 3 of those free tickets last time we did this talk. So stick around, keep coming to meetups. We're going to have cool talks and free stuff for you. Part of the free stuff we have for you is the code for Graph Convolutional Networks. You can find it on a repo, which is mentioned later in the talk, and I'll say it again. That's me. That is Steve. He also works for Expero. He gave a talk like this, much less sarcastic than this talk's going to be. So if you're less into sarcasm and more into content, go to YouTube and check out his video. These slides will all be somewhere or something. Those wonderful ladies in the back will tell you where that's going to be. You can click on that link, and again, you can see all this stuff for review. With that, here's the agenda. So first, we got to cover Twitter. That slide's a little dated now, but I'm going to do it anyway. You're going to like it. And then we're going to go into the applications of what you can do with this methodology. We're going to talk about what is a convolutional neural network, which you've probably heard before. What is a graph? And then what is the intersection of those two things? What does that look like? Before we talk about Twitter, raise your hand if you're a data scientist. Okay. Raise your hand if you have built machine learning stuff. All right. And now raise your hand if you've built deep learning stuff. Yeah? Cool. Okay, we'll cover some of that stuff. If I'm going too slow, just tell me to hurry up already. Come on, let's go. Twitter, here we go. All right, so I used to give a lot of talks when Twitter was still at the 140 character limit, and I like to make snarky hashtags. Now they've gone to 280 characters, which means that my hashtags are ridiculously long now. So here we go. Graph Convolutional Networks are the best thing since sliced bread because they allow algorithms to analyze information in its native form rather than requiring an arbitrary representation of that same information in a lower dimensional space, which destroys the relationships between the data samples, thus negating your conclusions. That's also the punchline of my talk. So we're going to talk about why that is true and what it means to have relationships between data samples, which is why I'm going to talk about convolutional neural networks before I talk about graph. So, before we do any of that stuff, any technical stuff, what can you do with GCNs and related architectures? I'll mention 2 related architectures because we had a request for that. Here's a Facebook ego network. That means one uses, this is really timely actually because of Cambridge Analytica. I definitely should have dusted off this slide, but here we go. You can come to your own conclusions. Here is one Facebook user's ego network. So this is all of one Facebook user's friends, their relationships, the links, and this is a graph by the way. The left-hand side graph is unstructured. It's just all of the data just plotted arbitrarily. That's a forced vector layout. And on the right-hand side, we've used a community clustering algorithm to group the nodes in the graph, so those are friends of this person, by their political stance. And we've populated those political stances using a graph convolutional network. So again, very timely. I promise I didn't prep this because of Cambridge. But you can, if you know about, and we already know this because it's been in the news for the past 2 weeks, but if you know about your friends' political stances and some other things, then you can infer political stances of that user and of other users inside of that ego network. So those are called alters in the parlance of Facebook API. Here's another thing you can do. This on the right-hand side, the rendering is junky because the resolution is lower. On the left-hand side, we see some of the edges in this graph, but this is a highly interconnected graph of entities, in this case individuals, that are all associated with one bank. They all have either accounts with a bank, mortgages with a bank, loans, credit cards, something like that. And the edges, which you can't see, are financial transactions between those entities. So each one of these nodes, again, is a person. And we've popped open one of those nodes on the right-hand side to show transactions. This is money flowing to some account. And those accounts may or may not be held at that bank, right? That could be merchants too. The idea is, can we do fraud analysis in a more accurate way using graph than not using graph? Because many of you have probably already played with fraud problems where you say, hey, here's a couple of examples of fraud. These transactions look weird because the dollar amounts are over X or whatever your random forest tells you. And have you guys used Lime? Sidebar. Anyone use Lime library? It's a library for prescribing, attributing causation back to your model. If you haven't checked it out, it's pretty cool. I'm just starting to learn it now. Sidebar over. We're back to fraud here. If you want to know why fraud happens, check out Lime. But if you want to use or leverage the power of the connections in your data and not just the samples of data themselves, slap them in a graph and then use a graph convolutional network. So let me reiterate that last part again, because that again is the punchline. That's my Twitter hashtag. There are connections. Again, you can't see them in this graph. But in this graph, you can kind of see them. Edges, connections between people. And there are also properties of those people, or properties of those bank accounts or whatever. And as we've popped up on the right-hand side, those properties could be financial transactions. So we're going to use this technique to power our analytics using not only information on samples or entities, but also connections between those entities. Okay, so you could do a whole lot of cool stuff with a convolutional neural network in 2014 and or 16, and you can't use that same architecture on graph. So that is your robot, your CNN, working on graph and failing miserably. The reason you can't do that is going to come up in section number 2. I also put this in there. Sorry, this rendering again is bad. But this is a different type of architecture called a graph autoencoder that is sticking 2 of these graph convolutional networks back to back, just like a regular autoencoder, except that you use graph as inputs and outputs. And here we're predicting a shipping route that is not currently used in a supply chain. So that predicted shipping route on the karate network, I put it in there, is so like send your trucks this way because you're going to save gas money. That's absolutely obvious in this example, but if your supply chain is like 25 million trucking routes or combinations of trucking routes, it's not that obvious. So here we go. I apologize to all the deep learners in the room because you probably already know this stuff, but I am a physicist originally, and so I want to go through the math. So yes, you're going to see equations, but you're also going to see GIFs. You're welcome. That's a convolution. That is the equation for one-dimensional convolution. And there is a GIF of 2 box functions, sometimes called rect functions, sliding across each other, summing and multiplying, which is convolution. The minus sign, by the way, in the convolution, for those of you who are interested, basically means that that is the same thing as a correlation. You just take one of the signals and flip it. Here is a 2D convolution. And this one I actually want to show another sweet GIF for because, you gonna do it? Yep. Because this is important for the image analytics tasks that you all are doing. And for the people who have not built deep learning architectures, this is a pretty nice description of how convolutional neural networks do their thing. So you see those patches sliding across the data. Those are convolutional kernels, so-called kernels, and they slide across your images as the network operates, and you get outputs for each of the kernels. And then you have another operation called pooling. We don't care. Half of you in the room already do this on a daily basis. We're going back to the presentation. So, who cares? Well, I'll tell you who cares. Cookie Monster cares! Because I wanted an image to show you how these things operate, and I found an image of Cookie Monster. So, again, you're welcome. Here's a 2D convolution. This is discrete. It's also chopped off on the side because of whatever. This is the same. This is the equation that I had on the last slide with the boxes moving across the data. Tick, 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 tick. This is the discrete version of that equation. That's what you actually use on images, on real discrete data. So if Cookie Monster is an image, we pop Cookie Monster into this convolutional neural network that I scraped from the web somewhere, image, CCBY, and we iteratively convolve, downsample, convolve, downsample, and then eventually get to a flattening layer that says, yes, this is a picture of Cookie Monster. Oh, look, I have the pooling equation on there, too. That's like a downsample operation, sort of. It's kind of hokey. Okay. Here's a slide you've seen many times before. This is why do convolutional neural networks work better than multi-layer perceptrons, just linear feed-forward networks. This subject has been covered so many times, it's like what? Beating a dead horse. So let's analyze an image of a dead horse, shall we? So when we look at this dead horse with a convolutional neural net, I told you it was going to be sarcastic. When you look at this image with a convolutional neural network, you do the same thing I described with Cookie Monster. You convolve, you downsample, convolve, downsample, finally you get to an answer. You could do that without the convolution operation by flattening the image first. So if you just took the pixels and stripped them apart and put them, like truncated them back to back in a 1D array, you could input that into a feed-forward neural network, and you could, presumably, also make a classification. The reason that people with money, e.g. Google, Amazon, Facebook, whatever, don't do it that way, and they use convolutional neural networks, is because when you flatten that image, you're destroying information. So in this image, this is a 2D array of bits. The pixels have meaning. Their spatial relationship has meaning. So each one of the points in this grid, on this image, on this array, is related to the point next to it, to the pixel next to it. And when you destroy those relationships, you lose information. My hand-wavy conjecture is that if we already have our data in a graph, we are representing that information in its optimal way if we set up our graph right. So again, we're moving from a 2D image to something that's sort of n-dimensional, let's say political stance. That's a multifaceted characteristic. But if we were to say we want to describe our political stance on a regular grid, let's say Democrat, Republican, some gradation between the two things, we're destroying information because there's many levels of other stuff that can go into that, right? How liberal are you? How fiscally conservative, socially conservative are you, right? So when you arbitrarily force data into a grid or a semi-grid that is not conducive to the information, you lose power in your analytics. And that's exactly the same thing that happens when you try to analyze an image with a not 2D system like a convolutional neural network. So that's CNNs. What is graph? I don't know where this image came from. I found this image on my computer, so I'm calling it a narcissist nanograph. No idea what I was doing with it, but it's got my name and my initials all over it, so that's cool. Each one of these, each one of these red dots is a node, and each one of the connections between those red dots is an edge. So each one of the nodes can have properties like this says 2, this says ASDF. Those nodes could be images, they could be databases, they could be anything you want, and they can have multiple properties or one property. The edges themselves can have multiple properties. And again, those properties could contain things other than text labels. They could be images or anything you want. They could be other graphs, actually. So that's what a graph looks like. And that's a big blob of stuff, which is also a graph. Don't know where that image came from either, but that is a bunch of nodes that are connected by a bunch of edges. This is what a graph really looks like in, maybe I shouldn't say storage because the triple store people in the world, in the room are gonna hate me. But this is called an adjacency matrix. This is the graph the adjacency matrix corresponds to this graph. So our color bar here says white pixels are 0, black pixels are 1. If you have a black pixel, it means 2 nodes are connected. There is an edge there. And a 0 means there's no edge there. So let's look at this. 0 node is connected to 1 node. So if you go to the 0 node, that's connected to the 1 node, black 1 pixel. 0 is also connected to itself. Self-connections are a thing. The 0, 0 node has a 1 pixel. Cool? Got it? That's an adjacency matrix. Which things are connected? How are they connected? Those adjacency matrices don't have to be binary. You can have weights, like you can have real values inside your adjacency matrix. But when we look at increasingly large graphs, we increase the size of our adjacency matrix as n squared. N nodes, n squared, because you have to have 2 axes to represent that. In all of these cases, in fact, we have symmetric matrix, so you could store half of this information, because if 1 is connected to 2, 2 is necessarily connected to 1. But there are graphs called directed graphs, so you could have a situation where you have 1's connected to 2, but 2's not connected to 1. In that case, your adjacency matrices are non-symmetric. But you can see these things get out of control very quickly. 800 node graph is like you can do nothing with that, it's tiny. Here's how you analyze an adjacency matrix, a graph for real. And I'm using the word isomorphism here. I don't know if we have any mathematicians in the room, but I did want to throw some group theory in with this graph theory. This is the question, are these 2 graphs the same? That's an NP-hard problem. And it turns out to be very difficult to solve it, even in approximation. So here's the same graph we saw before. Here's its corresponding adjacency matrix. Here is the same graph. Actually, let me redo this part. We're saying that this is the adjacency matrix only if we sample clockwise from the upper left node. So we start with node 0, and we put that here. 1, 2, 3. We're going this way. That's the adjacency matrix. This is the same graph with different labels. There's Cookie Monster again. And we have some text labels and some mixed integers and things. So if you were to compare the labels on those nodes, you would not find that those 2 things are the same graph. Unless you built something that said, okay, so if adjacency matrix pixels are exact match, that's an isomorphic system. All right, so that's easy. But then you run into cases where you have non-conservative systems like this cyclic permutation. Same graph as this, except in this case we've rotated the graph clockwise 90 degrees. We're still using the same sampling operator from the upper left node clockwise, and we have a completely different adjacency matrix. It's very difficult to tell if this adjacency matrix is the same as these 2. These graphs are all the same. In the 4x4 case, obviously you could do an exhaustive search, but again, that quickly spirals out of control. And it spirals out of control at an NP-hard rate. So, here's a perturbation of a graph. These 2 things are not the same graph. We've destroyed 1 pixel with what looks like a very shoddy PowerPoint job here. And when we destroy 1 pixel, and its corresponding symmetric pixel, we completely change the structure of this graph. I mean, to the human eye, these 2 things do not look anything alike, and indeed, they could represent completely different types of systems. For instance, this could be normal transactions between whatever restaurants exchanging money. This could be a money laundering ring. So, 1 pixel changes, the entire system is different. That's important because the same thing is not true of a regular image. A la this slide. Okay, so we've changed some pixels in that image, yet we can still tell that they started as the same thing. So we've got dead horse faces down here, human faces up here. We can still tell that these started as the same image, right? And we've changed a lot of pixels in this image. By the way, if you haven't played with neural styles, check it out. It's awesome. You take an image and you stylize it using the convolutional neural network, and you can like give it examples of styles that you're interested in, and then an input image, and you can do cool things. So that's a picture of me and my friends mixed with a Mandelbrot fractal, and then of course mixed with dead horses. So dead horses aside, it's very easy to tell these images are different but related. I bet you no one in the room can tell me which pixels are different in these adjacency matrices. And that is only an 800 node graph, which again, don't try to do anything in the real world with 800 nodes. Here's Euclidean spacetime. We're getting there. We're still on graphs. We're about to get to graph convolutional networks. So in Euclidean spacetime, we can define a so-called metric. That is the distance equation that you all know, because the shortest distance between 2 points is straight line. There you go. So that's the equation of a straight line in Euclidean spacetime. Shortest distance between 2 points. Define a flat spacetime metric. Minimize the distance between 2 points. We can do the same thing in spherical space. There it is. That's the line equation, if you want to call it that, in a spherical space. In fact, it turns out, so that's called a great circle, by the way. So the reason that airplanes have the cool archy patterns on the airline maps is because those are great circles. Those are actually, that's really the route that those airplanes fly. Anyway, doesn't work in graph. My computer doesn't work either. So the reason that this doesn't work well in graph is because graph represents sort of a non-continuous, non-differentiable space-time. Oh, yeah, that's right. Okay. Sorry, we're on small slides here until we reconnect. This is awesome. So this is a representation of some example that I just threw together of a non-continuous, non-differentiable space. So you can see there's nasty holes in this space, and there's self-loops and stuff. Here's a graph that exhibits all these characteristics. So we have nice properties in nodes 1, 2, and 3, but node 4 isn't connected to anything. So there's your holes in the space. And then node 0 is connected to itself with a self-loop. So, how are you going to define space? How are you going to define a path in a space that isn't really a space, in a space that has holes in it and self-loops and stuff? The reason I mention that is because you can't define a standard convolution operation on a space that has holes in it. Let me see if I can redo this. All right, we're doing it from the phone, people. We're hotspotting it. That is a crazy x-dimensional thing, which is just some random graph that I had populated again, on my computer. And I'm showing an adjacency matrix, and I'm trying to ask the question whether or not, it's awesome to do this when you can't see your, oh, hi. When you can't see your fingers. I'm trying to ask the question, can we map this graph down into a space which is something that we can perform convolution on? The answer is yes, you can do that using a variety of techniques called embeddings. Embeddings can happen in probably an infinite number of, actually yes, necessarily an infinite number of ways. The two ways that I'm showing on this thing you can't see are using spectral embedding, so-called spectral embedding, which is an eigenvalue decomposition, and also principal component analysis. Did it work? Hey-o! So we start from the graph. We build an adjacency matrix, or that's already really defined when we define a graph. Then we embed into 2 dimensions the graph structure using 2 different methodologies. And once we've done that, you're in 2D, and you can do convolutions all day long, and that's cool. And you can use graph embeddings to do machine learning workflows, deterministic analytics workflows too if you want. But that's out of scope for this talk. It's simple. You just use all the algorithms you're already using. You just apply them to that embedded space. Here's a linear convolutional kernel. We're offline again? Come on. This is my Taylor Swift joke. Oh, man. Okay. Well, we're offline again, but this is... There you go. Here's the Taylor Swift GIF. That was me mashing up Taylor Swift songs with Winston Churchill's We Shall Fight Them on the Beaches for the best mashup of all time. You would do that with a linear convolution. I don't know what I'm talking about. You could do spherical convolution on something like a globe if you were trying to mix two spherical signals. But again, on graph, you can't define a standard convolutional operator. I will claim that you can build a kernelized version of a convolutional operator to operate on specific graphs, specific types of graphs even, but not general graphs, because again, you have this, every single graph has a different information space with holes and self-connections like I showed before. All right, that's why you can't do it with a convolutional neural network. Let me tell you what a GCN actually is. So, this is the equation for the GCN. This is the whole presentation right here. We could have just skipped everything else and gone straight to the slide, but then you wouldn't have gotten to see Cookie Monster and Dead Horses. I know you enjoyed that. Okay, so this is layer L plus 1. This is layer L. So at layer 0, which is input, this H matrix is your input, maybe the X matrix in scikit-learn parlance. The W's are your weights. Those are your trainable parameters. No, I don't have a bias term in this layer equation. Yes, you can put one in. This is the adjacency matrix we talked about before. D is called the degree matrix. That's the number of connections that attach to each node. So if you think about that, you just have a diagonal matrix. All other elements, the off diagonals are 0. The hats just mean those are normalized with a standard I matrix, identity matrix, and they're normalized by this reciprocal square root thing. There's an activation function here. Use whatever you want. I think I'm using leaky reloads in the demo I'm going to show you. But that's it. So every time you go to another layer, you propagate all the information through this equation. I'm hoping I get a question about that when we get to questions. Okay, so these are images straight out of the Kiff and Welling paper, who were the ones that described this process. These are the input feature maps. So you can see the stacks going into the screen direction. There's as many maps as there are features. So basically, like as many graphs as there are features, but really it's just another matrix you have with all the properties stacked up. The outputs of the GCN are feature maps. These are your targets, so like one hot target vector, basically. And then here's a description of how the thing works. I don't know, it's not a good picture, but I wanted to put it in there because they wrote it. That's what it looks like. So all you deep learning folks like to see these architectural diagrams that look like this. Yeah, I only have 2 layers in there. Is that real? Plus dropout. Is that real? Yeah, that's actually what we did. So all the analysis you'll see in this talk and in the demo, I'm pretty sure, it was just using a 2-layer graph convolutional network. Easy peasy. You have the graph convolution, which is the equation I showed above. Activation, dropout, do it again. That's the whole network, folks. I have a softmax classifier at the end. Yeah?
The A, you said it was just the adjacency matrix, or did you do some processing to do PCA or the spectral stuff?
Nope, this is the so the spectral embeddings, the PCA embeddings, those are completely different. And if you don't want to use GCNs, you can perform analysis on graphs.
Is there anything you have to do to make that canonical, or like you said?
This equation?
No, the A, just the adjacency matrix.
All that's done here is just to add the identity matrix.
There's n different ways to represent a graph.
Yep. That's right. And I claim that no matter how you sample your graph, like that linear clockwise rotation operator for sampling. However you sample your graph, you're still going to come up with targets that are the same every time.
So it's rotationally invariant.
It's rotationally invariant, but it's also everything invariant. This equation obviously doesn't care about the positioning of the adjacency matrix because these things are normalized by the degree matrix, and then more important is that those trainable parameters start as random floats, right? So you could, I mean, same thing with images, right? You could flip an image or rotate an image, and if you train on that, you still come up with the right classifications, as long as your labels go in properly. Yeah.
So if A is the adjacency matrix, then what is H?
H is the, at layer 0, it's input, which is your features. And at every other layer, it's the output from the previous layer, just like any stacked deep neural network. That's how it works. So I don't know if you guys are familiar with TensorFlow. For whatever reason, we did this in TensorFlow. This is just building placeholders for your data and your labels. Here are the trainable parameters. This is only one layer, by the way, just to show it. Here's the good stuff. This is where the actual math happens. 1, 2, 3, 4. So again, that's just a simple matrix multiplication, activation function. Do it again. And all this stuff, loss function, you know this all. Optimizer, and then run the training. Super simple. How many lines? It's 4 lines of code to do the actual guts of the thing. So that's pretty impressive. Here's the results. So, bottom right-hand table, those are Kiff and Welling's results. The paper is linked. Again, get the presentation from them and you can read it. You can just search it on Archive, you'll find it. These are our results, and they correspond pretty well, actually. We did our own testing, runtime testing, on a real problem, which was a credit worthiness assignment. So we had some bank customer data we analyzed to say, are these applicants qualified for a small business loan? The data that these guys used in the paper was pretty small, 0.5 meg. The data that we used also was pretty small, 350 megs. But we wanted to get a little bit more meat in there to see how the thing performed. All of my tests were run on an NVIDIA V100, which is so nice, just so nice, people. I can't tell you how fast things are running. Okay, so pretty good. 14 seconds using a straight feed-forward network. That's, again, the thing where we just strip apart all the information and stack it into one vector. And then using the GCN, we have a much longer runtime, as you'd expect, and we have much higher accuracy, as you would expect. Again, we're preserving the structure of the information when we use GCNs as compared to definitely this feed-forward network junk, but also spectral embeddings or some other things that I won't talk about because I'll get lost on another tangent. You can't see the stuff that's behind these images here, but those are the things we've done today. And then there's okay, I deleted my thing. Anyway, there used to be like a million ideas behind that. That was just some stuff I'd been thinking about for 5 minutes. This stuff is widely applicable. You can do a huge variety of analytics tasks on basically any system you can think of. You can think of an image as a graph. It is. It's a regular grid, right? So that's a graph. You could perform this analysis. It would be foolish to do so, obviously. But you can formulate most problems as graphs, analytics problems. I won't go through any more, boring you. It's demo time! You can't see the architecture, resolution's bad, but that was the TensorBoard depiction of the Graph Convolutional Network. Might be able to pull it up. Probably won't be able to see. Here we go. All right, so we're going to run it. There we go. This is on the little tiny data set, half a meg. Oh, done. Okay, so once we have finished training, we see our accuracy scores and our times. Let's see what it looks like in our visualization tool. Yes, JavaScript, I'm sorry, deep learners. So sorry. Although, I was working on a project recently where we did deep learning in the browser, just the inference pass, using a library called deeplearn.js. It's pretty cool. It's a little clunky right now because you have to like redefine your model, even at inference time, but it's worth checking out. That's what happens when you do a live demo. There we go. What's this? Yeah, cool. That's the wrong demo. So let me talk about this demo. That's awesome. When I came in here, I realized that I hadn't run the demo on this computer, and there you go. So this relates to graph analytics. Oh yeah, we can do this now. Okay, so this is a fraud. This is the money laundering thing, right? So this is using, instead of individual fraud, we're talking about organizational fraud. Can we discern organization, like organized crime, like money laundering rings? So if you've got a graph of individuals, arguably, you don't even need a graph structure to discern whether or not some of these transactions are fraudulent. If we want to, if these connections are fraud, connections are monetary transactions, we can perform standard analytics techniques, logistic regression, whatever, to train a system to learn if these are fraud or not. But if we're interested in like analyzing a group of entities exchanging money, we can use the graph analytics paradigm to perform that analysis, because you have information about all the nodes, which potentially are businesses. You have all the information about the connections, the edges, which presumably could be like multiple transactions or transaction types or something like that. You have their relationships all to each other. So what we found and what this demo shows is not a GCN, but it is a graph machine learning widget which analyzes the topology of graphs. So it extracts subgraphs like what I've circled, and then it says, find all these metrics about the geometries of this graph. Like for instance, in that case, there's 3 nodes that are connected. There's one, it's a degree 2 graph because there's 2 connections per node. You do many of these things, eigenvector centrality, and then you insert all of those topology metrics into a classifier of your choice and let it rip. So we've labeled a couple of instances here. All the blue ones are not, these are all businesses, are not related to fraud. These red things, this is such a good setup here, are entities that we have determined are related to fraudulent transactions. I am just going to get out of here because I absolutely cannot control this. All right, so that was another aside. All right, so we have, that's it. We have all these examples about the things that Expero does with graph. So this is financial analysis. We build all this stuff from the analytics packages, the graph database, the UI, everything. We do the whole stack. This is a graph system where we're scoring risk, commercial real estate buyers on their risk scores, like based on their previous account history. And we use a graph database to do that because you have all the connections between the properties, the buyers, the sellers, all this. So that was cool. That is, I don't know, another graph thing. And obviously you don't need to in most cases you don't visualize the actual graph when you perform graph analysis because you don't really care, right? You just care about the properties of each one of the entities. That's it. Questions? Yeah.
I noticed your adjacency matrices were all 1s and 0s.
Yep.
Could they also be integers or floats or complex or?
Yep, they could certainly be integers, reals, complex numbers, but they could also be images, audio, databases, other graphs.
Oh, adjacent point can be an image?
Yeah, so depending on how you want to define the term adjacency matrix, yeah, you could build, instead of like a 2D array, you could build like a 2D database and store that information in there. Is that useful for the GCN? No, but in many cases it is useful for like data.world, I think. Yeah?
In the creditworthiness example, what accuracy metric are you using? Like, I guess in the sense, I'm thinking like, if your data set is imbalanced, then that 70% accuracy could just be like, I'm predicting all zeros.
Yeah. It's highly imbalanced. You have to take care of that. It is also, so we included demographic information in that context because that's what the bank wanted to do. And actually the punchline of that process was that this system that we built was disproportionately disapproving female small business loan applicants. So we went back and teased out that problem in detail. And in fact, we found that it was, 1 in 10 women were approved for small business loans, 1 in 3 men were approved. The cause of that imbalance was 100 years worth of bank loan approval officers doing that, right? So we actually went back and we fixed the problem. So we rebalanced the data set and we fixed the bias in the data set as well. So yeah, we used demographic information, we used financial histories, we used, all the stuff that banks use. And then the targets were the assignments from human loan officers. Anyone else? Did you understand the question that I was trying to provoke from the audience when I said the thing?
Which? No.
What was it about? I don't even remember myself anymore.
D in your equation, I think. Keep going.
There we go.
There.
Yeah. Okay.
Excuse me.
Yeah.
In the applications you have mentioned article assignment. So what's that?
Article assignment?
In the applications.
I'm sorry, I didn't.
In the applications slide,
Uh-huh.
you have mentioned article assignment.
At the end? This thing?
Yeah.
Article assignment. So that was like paper classification. So semantic parsing. So classifying, this is a paper about zebras, and this is a paper about genomics research.
That we can do with the text as well, right?
Yeah, so you don't actually need, my claim here is that rather than actually doing semantic parsing in NLP tasks, if you had, much like the Facebook example of Cambridge Analytica, you know something about the relationship of the papers to each other, right? Because you have references at the end, and then you also have citations moving the other direction into that paper. So you can build a network, a graph of paper references to each other, and then you can say with high degree of confidence, this paper, just because of those relationships, this paper is about beekeeping. Wait, let me see my thing. Okay, this is, this architecture, the Graph Convolutional Network, right now, is highly inflexible because you saw me train the thing in real time, right? On that little tiny data set, the code was running. At the same time, I was also calculating accuracies. You might have seen the output. You can't change the structure of the graph after you've trained the network. Because think about it. So you have these inflexible matrices. You have these grids of things you've defined as adjacency matrix, degree matrix, whatever. And at inference time, you have to perform inference on the same structure that you perform training on. So we were talking earlier, I think 2018, you're going to see a lot of literature about this. This is a hugely powerful process. I mean, you saw the dramatic increase in accuracy. It was like 12, 16% just flipping architectures. Because you include the connections between data points, but we have to solve that problem. And let's do it. The code is open. Let's submit a pull request, guys.
Are you talking about the size of the graph itself then?
Yeah, and not only
Just
this.
add it to the maximum size.
you could do that, but you wouldn't be providing any more information. Because, for instance,
You'd have empty nodes.
yeah, so okay, so let's take the instance where we don't, same graph size, but connection has moved, an edge has changed from node 1 to node 7 or whatever. You have trained this network on the connections and the nodes within one specific, yeah. So it's like this cast concrete thing, and if you change anything, you break it, you break the mold.
Well, A is an input then.
A is an input, yes, indeed. To change the output, even at inference time, if you change A, you have to retrain the network.
It's a whole different architecture.
Yeah. Which is a bummer.
So you can't use the model to train future data?
So, let me not put you all to sleep by dragging you down in the weeds. But yes, of course you can. So you don't know anything about whatever 30% of the nodes in the network. When you run this thing, you train it on the full network, and you have a mask, like a zeros mask, when you input this, which I didn't show in that little code snippet. And at inference time, you remove the mask, and you let the thing propagate labels into the network. So yeah, you have to. But if you were working in a temporal setting, like an online setting, this would not be an architecture that you could use, or presumably you wouldn't want to use. So this would be offline only.
What you're saying is a dynamic graph that's continually having new edges and vertices added. Okay.
Yeah.
It won't work for that.
I'll leave you with one last snippet. My idea about how to fix this problem, which is totally untested and is just conjecture, is that you basically perform a subsampling operation, like batching, like mini batching on graphs is a really complicated thing to do, because if you're like slicing nodes out of a graph, you're totally changing the structure. But I think that I have this intuition that if you use a smart sampling operator, like sample communities, so for instance, if you do community clustering where you have high density of nodes inside the community, but very low density of edges outside that community, you can safely sample and train and test. And you do that iteratively and build up like a meta model. I have no idea if that would work, but I want to do it. Pull request, everyone, come on. That's it. Thanks for coming.